All right, ladies and gentlemen, class recording has started. All right. No, I just said ladies and gentlemen. So.
Can you say good morning?
I'd rather not, because it's not morning. So. How about good afternoon, ladies and gentlemen? Class recording has started.
No.
All right. Over the past. Thanks for noticing. All right. Over the past couple of days, we have been working on this this outline that I have titled the quote-unquote location of electrons in the quantum mechanical model, right? Based on Heisenberg's uncertainty principle, we don't know exactly where electrons are, right? But based on Schrodinger's model, we do know what? Probable locations. We call those probable locations orbitals, okay? And as we talked about, right, and this is probably about the 15th time, but just real quick as a review, right? Every one of these locations is an orbital, right? But we need to distinguish them from each other somehow. We do that by what?
Addresses.
Quantum numbers, right? Quantum numbers. Quantum numbers are those quote-unquote addresses, how we distinguish all of those orbitals from each other. How many quantum numbers do we need to distinguish each of those? A set of 4. Each orbital has a unique set of 4 quantum numbers. And actually, I guess we should amend that statement a little bit. The 4th quantum number we talked about yesterday actually really tells us more about what? The electrons within those orbitals. We said that each orbital can only hold how many electrons? 2 maximum. Okay? So, yesterday, right at the end of class, I gave you this exercise here, and I gave you 4 electrons. There's 5 on the paper because we did this one on the right together. But the exercise was to come up with a set of 4 quantum numbers for each of these electrons. First quantum number, principal quantum number, letter N. What does the principal quantum number tell us, essentially? It can tell us 2 things. Distance from the nucleus, but what does that relate to? Energy, right? So it basically tells us the energy level that this electron is in. Second quantum number, the angular momentum quantum number, letter L. What does the angular momentum quantum number tell us? The shape of the orbital, right? And so far we talked about 3 shapes specifically, right? What's the first shape that we run into? Sphere. We call that what kind of an orbital? S orbital. What's the next shape? Double teardrop, and we call that a p orbital, right? And then the third shape was 4-petaled flower, and we call that a d orbital, right? There are f orbitals that we didn't talk about, but they're pretty complex and hard to draw, but they do exist. Okay? I can get you like a model of it, but I don't have it with me. Sorry. Maybe on Thursday I'll get it for you. All right, letter M. The magnetic quantum number. What does the magnetic quantum number do for us? Orientation, right? If we have more than one orbital that is the same shape, how do we know which one of those orbitals we're talking about? And we said specifically this is good like for p orbitals. There are 3 p orbitals. One on the x-axis, one on the y-axis, one on the z-axis. Which one are we talking about? Joe, go ahead. Because -1, 0, and 1, we talked about that when we're determining the values for the magnetic quantum number, he's asking a question.
I knew you were finding it.
I was actually literally answering the question. We talked about, Joe, the idea that the possible values for M run from -L to +L, okay? And so that means that we limit the number of values of M, the number of orientations there can be based on the shape. So L is a shape thing, right? And we said that for p orbitals, L is equal to 1, okay? If we run from -L to +L, -1, 0, +1, that's a maximum of 3. And there's a maximum of 3 p orbitals. For d orbitals, L was assigned a value of 2. -2, -1, 0, 1, and 2. So, not artificially, we have limited the number of possibilities for M to the number of those orbitals that exist. We could call them 1, 2, and 3, but then it's just something that you kind of have to memorize. Like, well, how come M couldn't be 4 if you're talking about a p orbital? Well, because there aren't 4 p orbitals. But if you limit it to -L to +L, we limit the number of possible values of M to the number of orbitals that exist of that kind. Okay? Is that good? Okay. And then finally, right, we ended with our S values, and we said, what does the S value do for us? Describes which electron we're talking about, right? Maximum number of how many? 2. Okay? Are we okay with this picture? Are we okay with this exercise that we went through right at the end of class yesterday? All right, this is complex and not easy to decipher, especially if we're talking about the entire picture. All of these orbitals on top of each other, surrounding each other, mingling with each other, right? If we're trying to describe the location of electron within this picture, that becomes pretty difficult to do. So, like we do in a lot of cases, if we have something that is complex, let's look for ways to simplify it, ways to represent that complexity in a more simple way. And so we start off then with our orbital filling, orbital diagrams, and electron configurations. The presentation here is pretty boring. It's just black writing on a white screen because we're not going to do a lot of presentation. It's going to be a lot of writing and doing stuff. So if you're bored by this screen, then it's okay. We're not going to do a whole lot of it. All right. Orbital filling is governed by something that is called the Aufbau principle. You guys know the Aufbau principle because we have talked about something similar. Sorry. You know the gist of the Aufbau principle because we have talked about it in many situations up until this point. The Aufbau principle says orbitals are filled from lowest energy to highest energy. Why? Electrons close to the nucleus have a lower energy. Why does that happen first? Naturally, what do systems try to do with potential energy? Get rid of it. Lowest potential energy. When I hold the baseball up in the air, where does it go when I release it? Down. Why? Getting rid of potential energy. Less potential energy on the floor, more potential energy up on the top. If I dropped 100 baseballs in this room, let's go even more than that. Let's say like 10,000 baseballs. Okay? If I dropped 10,000 baseballs in this room, what would happen to all of them as long as they could? Where would they end up? On the ground. Because that's the lowest potential energy. When would they start stacking up on top of each other? If the ground was totally filled up, then they'll start stacking up on each other. But until that point, they will try to find that lowest potential energy. That's true of any natural system. It will try to get to the lowest potential energy that it can naturally, and if it can't get to the lowest potential energy, it will get to the next lowest potential energy. That's true of all potential energy throughout the whole universe. As we've discussed, orbitals closest to the nucleus contain lower energy, so those are the ones that get filled up first. Can we make an electron move from the lowest energy orbital? Can we get an electron to move out of the lowest energy orbital? Yes. We have to do what? We have to give it energy. We have to do what to it? We have to
Energy.
do work to make it move to a higher energy state. But will it stay in that higher energy state? If we continue to give it energy, yes. But if as soon as we stop supplying it with that energy or stop doing work on it, what will it naturally do? Fall back down, right? Get rid of that energy and fall back down. That's true of any state, and it's true of these as well. So the Aufbau principle says we fill orbitals from the lowest energy to the highest energy. These two charts you have in your outline. I prefer the one on the left, but the one on the right basically tells us the same thing. This is a representation of all the orbitals that surround the nucleus of an atom. Notice the left-hand side. I like the one on the left the best, so that's the one I reference most often. What does the left-hand side of this chart say? Increasing energy of electrons and orbitals. In which way is the arrow pointing? Up. So where are we going to read this chart from? From the bottom to the top, right? We want the lowest energy orbitals that we can find, and we're going to go from there. Good? Next. It'll make more sense after we do more of them. So, next, orbital diagrams. Orbital diagrams show the distribution of electrons within the orbitals. It is a shorthand representation of this drawing, basically, showing the distribution of electrons around the nucleus in those orbitals. We use either circles or lines or boxes to represent the different orbitals. Different books, different publishers use different representations, but we'll use one of these three things to represent the actual orbitals, and then we will use arrows to represent electrons. So an orbital diagram could look something like this, where we have a circle that has some arrows in it, or we have a line that has some arrows above it. These two things down here at the bottom, these are not actual orbital diagrams. These are just representations of what they could look like. All right, good there? For starters? Okay, let's start making some orbital diagrams. And we're going to start with the simplest orbital diagram we can find, and that one is hydrogen. So I'm going to go here, and I'm going to go to this, where I have the chart down here at the bottom, so we can reference it as we go along. First orbital diagram we're going to make is hydrogen. You'll see that in your outline, you have space to draw these orbital diagrams, like starting on page 2, or is it down at the bottom of page 1 where hydrogen is? Oh, it's down at the bottom of page 1. If we are going to draw an orbital diagram that shows the distribution of electrons around the nucleus for a specific atom, what's the first thing we're going to have to know? The atomic number. Why do we need to know the atomic number? That tells us how many electrons we actually have to place. Remember that the atomic number tells us the number of protons, but it also tells us the number of electrons. So we look on the periodic table, and you find the atomic number for hydrogen is what? 1. So that means that for hydrogen, we have to place 1 electron. Yep, down there at the bottom. Yep. So the first thing we need to do is we need to figure out how many electrons we actually have to place. Then we'll go from there. All right. Now that we know we have to place 1 electron, we have to figure out where it goes. That's where this chart comes in handy. So we said we're going to read this chart from where to where? Bottom to top. So we start at the bottom, and the first orbital that we run into is what? 1s. Okay? So we go here, we come up here, the first thing we run into is 1s. Based on the fact that we call an orbital 1s, you should probably be able to tell me 3 things about it. What's one thing you can tell me about an orbital, the fact that it is called 1s? N equals 1. What does that mean? Okay, it's the first energy level. Low energy. What else? It's a sphere. That's which part of it. The 1 tells us that it's low energy. What tells us that it's a sphere? The S. If it's low energy, what else does that tell you about it? It's close to the nucleus. Just by saying that there is an orbital called 1s, you know that it is low energy, close to the nucleus, and a sphere. And you know that because we drew this picture. All right? Well, not this picture. This picture. Okay? But, again, this picture is complicated. So instead of drawing all these orbitals on top of each other, we're going to shorthand it. We are going to draw, this is how I like to draw my orbital diagrams. There are other ways to do it, but this is how I do it. I'm going to start by drawing a line. And that line is going to represent an orbital. In this case, which orbital is that going to represent? The 1s orbital. To show that this represents the 1s orbital, I'm just going to label it as 1s underneath it. Now we have a representation of a 1s orbital. It's not spherical, it's not close to the nucleus, or at least not from this picture you can't tell that, but because you know these things, we know that that's what it's representing. What's next? What else do we have to show in this picture? An electron. And we said, what do we use to represent these electrons? Arrows. How many electrons do we have to put in this orbital? 1. So I'm going to take my red marker and I'm going to draw 1 arrow. And that is my orbital diagram for hydrogen. There we go. Okay? Well, it is the first one, so it's going to be a little simple, all right? All right, let's progress here, and let's do the next one. So if you flip over your paper, you'll see that the next thing we have labeled, I believe, is helium, yes? So helium's next. In doing orbital diagrams, the first thing we need to determine is what? How many electrons? You go to the periodic table, you find helium's atomic number. Hassan, what's helium's atomic number? It's 2. So that means helium has 2 electrons. The off-bow principle says that orbitals get filled from lowest energy to highest energy. Using this chart, like we said, the lowest orbital, or the lowest energy orbital we run into is which orbital? 1s. So, just to be a little different, just to show you that there's a couple different ways we can represent this. Here, I'm going to just draw myself a box. Remember I said that lines, boxes, circles can represent orbitals. I'm going to draw this box. What should I label this box? This box represents an orbital. Which orbital? The 1s orbital. So I'm just going to label it as 1s. Yes? Always go from lowest to highest. Okay? Well, hold on a second. Let's do this one first. Okay? All right. The spin quantum number, the last quantum number that we talked about yesterday, was important because what do we know about each orbital's capacity? 2 electrons. So how many arrows can fit in this box? 2. I'm going to draw my first arrow just like I did before. What were our possible values for the spin quantum number? Positive 1/2, negative 1/2, because we have to do what with those 2 electrons? Distinguish them from each other. Which electron is this? Which electron is that? How do you think I'm going to do that on this orbital diagram? 1 up, 1 down. There's my orbital diagram for helium. All right? Good there? Okay. Next one that shows up, I believe, on the sheet is lithium, yes? Lithium, how many electrons does lithium have? 3, because its atomic number is 3. Aufbau principle says that orbitals get filled from lowest energy to highest energy. Using this chart, what's the lowest energy orbital we run into? 1s. So this time, I'll draw a circle just to show you that they can be either one. It really doesn't matter whether we draw the line or whether we draw the box or whether we draw the circle. This circle represents an orbital. Which orbital is this circle going to represent in this case? The 1s orbital. So I'm going to write 1s underneath it. What do we know about the 1s orbital and its capacity? Well, how many electrons can an orbital hold? 2. So I'm going to draw one up arrow, and then I'm going to draw one down arrow to distinguish those two electrons from each other. Is this orbital full? This one's full. But have we placed all the electrons that we need to place yet? No. So we go back to our chart. 1s was always the first orbital because it's the one closest to the bottom. Moving up, what's the next closest one to the bottom? 2s. Knowing that it is a 2s orbital, what 3 things can you tell me about it? If I tell you an orbital is called 2s, it's a sphere, because it's what kind of an orbital? An s. What else can you tell me about it? It's farther than the nucleus from 1. What else can you tell me about it? A little bit more energy than the 1s orbital. How do we represent an individual orbital? With a circle. Which orbital, I suppose if you want to use rhombi, rhombuses, is it rhombuses or rhombi? Alright, here, what would we label this orbital? 2s. How many electrons do we have to place? 1. Question. Does it matter whether I draw this electron, this arrow, up or down? No. When is it important? If there's 2, then you got to draw one up and one down. If there's only 1 electron in an orbital, it really doesn't matter whether it's up or down. I usually draw up first just because, but if you want to draw a down arrow only, that's perfectly fine. Okay. All right. Orbital diagram for lithium. There it is. Rhombi, okay. All right. All right, good here? Okay, let's do one more. I believe the next one on your sheet is boron? Yes? Did I skip beryllium? Okay. So,
beryllium has feelings too. You know, beryllium, I bet, is a...
I'll tell you why. I'll tell you why.
It's definitely a female element.
Are you assuming the elements have...
All right. So, we go to the periodic table, and maybe elements are a matriarchal society. Maybe this is a male element. Maybe beryllium is a male element, and everything else is female. You know. Girl power, like. You know,
I'm not assuming. We just skipped over that.
All right. So, hey, this is recording, by the way. So, except you know, sometime. So, just throwing this out here, right? You know.
My name's Shane Burke.
So you're going to run for office one day, like, 30 years from now, and be like, this guy's a racist. Look at this, what he said back when he was 14 years old. Like, So, sorry, my bad. So now we, or he's a sexist, right?
Donald Trump can get away with it anyway.
No, let's not go with that attitude. All right, let's do better than that. All right, all right. So boron right? We go to the periodic table, we find that boron has 5 electrons. Okay? Or off-bow diagram says that orbital is filled from lowest to highest. Lowest orbital is always what? 1s. So I'm just going to go back to lines this time. And I'll call this one. If you want to keep using boxes or circles, feel free to do so. Yeah? 1s. What do we know about the capacity of this 1s orbital? 2 electrons. So we have an up arrow and a down arrow. Is that orbital full?
Oh, I see what
Yes.
boron, not beryllium.
So
Oh, yeah,
the next orbital that we come across is 2s. Right?
It's okay. It's not missing.
How many electrons can that orbital hold? 2. 1 up, 1 down. All right. So next, right, lowest to highest. What is the next lowest orbitals we find on this chart? They're not in the same column, but which is the next closest to the bottom? 2p. But what do we know about p orbitals? Okay, double teardrop shape. Okay, but how many p orbitals are there? There are 3. That's why there's 3 lines here. But what are you seeing about, well, there's 3 orbitals, right? There's an x-axis one, and a y-axis one, and a z-axis one. But what are you seeing about how far these lines are from the bottom of the chart? They're all exactly the same distance from the bottom of the chart. So is there any difference in the energy of an electron in the 2px orbital, or the 2py orbital, or the 2pz orbital? They're all exactly the same. That being said, when we draw them, we have to draw all 3 of them. 2p, 2p, 2p. Okay. What? No. Because how many electrons do we still have to put on this drawing? 1. So I'm going to put it right here. Do I need to put it right there? Not right now. And we'll pick up this discussion on Thursday.